second lecture. We are studying stochastic processes, and in this lecture we will study balance equation under Markov process. What is balance equation in a Markov chain? Right, before we study balance equation, let's have our recap of what we have been studying in past few lectures. Right, in last lecture SP21 we studied that the long-term probability pi of j is actually r I j of n, starting from some initial state I. What is the probability of landing at j at time n, where n is large? N is large. That we studied is independent of the two things. If n is large, it's not dependent on n. Rather, it neither depends on n nor on I. So it depends only on j. Therefore, we call it pi sub j. Right. In lecture number 21, we studied that this can be written as pi k. Pi k is the long-term probability of landing at k at time n minus 1, and this is the transition probability of going from state k to j in the very next interval, in the very next time interval. And this k, and we have to try it for all different values of the states m. This formula was studied in detail in last lecture, lecture number 21, and it is based on the Chapman-Kolmogorov equation that we studied a few lectures before. The long-term probability Rijn can be written as I. Instead of j, we have a k here, and we'll try all different values of k, but for time n minus 1, from 0 to n minus 1. And this is the transition probability from one previous time to the time n, from n minus 1 to n. Right. So in this lecture, I'm going to tell you that this equation number 1 is also called the balance equation. This equation that we studied in last lecture is called balance equation. Why do we call it balance equation? Balance equation for all possible values of the states, where m is the total number of states in the state space of our Markov chain. So for all states in J, this equation number 1 is the balance equation. Why do we call it balance equation? Because if we studied in lecture number 21, we studied that if the chain contains only one recurrent state and no transient state, then the long-term probability by j, it settles or saturates to a point as n grows very large. And we also studied in last lecture a normalization equation, that if it's a normal chain with having only one set of recurrent class with only one recurrent class, and the recurrent class is aperiodic, then the long-term probability of all states, if we add those together, they sum to 1. This gives rise to a stationary probability distribution, because we know that for a probability distribution, the sum of the probabilities of all events, they sum to 1. So normalization equations tells us that pi 1 plus pi 2 plus pi 3 plus up to pi m they all sum to 1. Right. In order to better understand what balance equation is, let's solve an example. This example was studied by us in a couple of lectures before. Now, this Markov chain contains only two states, so M, the state space, is 2. There are only two states, M is equal to 2. And these are the transition probabilities P11, P12, P21, and P22. Right. So, balance equation, I have written the balance equation once again, but with the difference that I have put 2 here instead of M, because now in this state, in this Markov chain, we have only two states, and for j equals 1 and 2. So we will evaluate pi 1 and pi 2. We cannot evaluate pi 3 or any other value of pi because we have only two states, 1 and 2. So this is valid for all 1 to M. So M is 2 here. So j would range from 1 to 2. Right. So how would we compute these pi's? Let's put 1 here. Let's compute the long-term probability for state number 1 for this state. Long-term probability for this state. So instead of j, we'll put a 1 here. So it would be pi 1, pk1, and pi k. And k would range from 1 to 2. So pi 1 would be this. Instead of j, we have put a 1 here. Pi 1 summation from k1 to 2, pk1 because j is 1, and pi k. Right. If we expand this expression, this becomes p11 pi 1 plus p21 pi 2, putting the values of k, both values of k1 and 2, and then adding. And then we can use the same equation, the same balance equation that we have written here by putting j is equal to 2. So we put a 2 here. So put a 2 instead of 1. J is equal to 1, put j is equal to 2. So it will be pi 2 is summation pk2 by k. Right, pk2 by k, the same. Right. And then if you put the values of k 1 by 1, and then 2, it comes out to be like this. And we know that for this chain for which we are working, P11 is 0.8, P12 is 0.2, P21 is 0.6, P21 is 0.6, and P22 is 0.4. So if we put these values in here in equation number 2 and 3, in equations 2 and 3, the new equations become 0.8 pi 1, 0.6 plus 0.6 pi 2, and this pi 2. Right. So an interesting observation is that equations 4 and 5, this equation and this equation, if we solve them simultaneously to find the values of pi 1 and pi 2, because it seems that there are only two linear equations, and we have two variables to solve. So we can easily find the values of pi 1 and pi 2. But if we try to solve them, we reach to a value that yields pi 1 is equal to 3 pi 2 from both equations. Why? Because they are not independent equations. So for simultaneous equations, if you want to solve two equations to find out the values of two variables, the two equations should be independent. But unfortunately, they are not. They are dependent. Therefore, we reach to the same result, pi 1 equals 3 pi 2. And we are still not able to find the values of pi 1 and pi 2. So what should we do then? We should make use of normalization equation that we have written before, and we have also studied this equation in our last lecture. Oh yeah, here it is. Normalization equation says that for all possible states in the state space, if we add the long-term probabilities, they sum to 1. So if we add these pi 1 and pi 2 together, they sum to 1. So now we have equation number 6 and equation number 7. They are two linear equations, and we have to solve them for two variables, two unknowns, and fortunately these two equations are independent. So if we solve them, put the value of 3 pi 2 here instead of pi 1. So we get pi 2 is equal to 0.25 and pi 1 is 0.75. This is the same result we obtained when we plotted these values, and I wrote a MATLAB code for that, and I also wrote a MATLAB code for that. This pi1, it started from a higher value and settled at a lower value, and pi2 started from a higher value and settled at a value 0.25, higher value compared to its starting value, and our and pi1 settled at 0.75. The same result we obtained using the MATLAB code I wrote when we were studying different states using equations. This is some kind of equations, right? And I wrote MATLAB code for that too. So you can go back and check in the previous lectures that we reached the same conclusion when we wrote a MATLAB code for that, and that MATLAB code was general, and you can ask me for that MATLAB code, right? Okay, so that's all for today's lecture. In our upcoming lectures, we'll keep on studying more about Markov chains. Thank you.